place was Yorktown, which is one of our research labs of IBM. And the game was Jeopardy, which is a quiz show that is running in the US for many years. And the two players who played against the computer were Brad and Pete, who are known winners, who won several times the $1 million, which means they repeatedly were quick and smart and knowledgeable and answered very quickly to the questions and knew how to play the game very, very well. And the game, as you might have seen, was about being able to answer a very cryptic question. So you get a question, and you actually need to treat it as an answer and to find out what was the question. And a simple question that I believe most of the audiences, when I ask that in Israel, know the answer immediately would be an Israeli general known for a part of his body. Oh, I thought it, maybe here I'm wrong. Moshe Dayan, an Israeli general who knows for a part of his body. That's the very simple question. And the answer is the question, who is Moshe Dayan? And that should be the answer in the Jeopardy game. And you can pick categories and so on. And what happened is that IBM signed an agreement and participated in the game in live show in 2011 and showed that a machine can overcome these very cryptic questions, understand free text and natural language, and be able to be quick and answer correctly to the questions. And that's what happened back then in 2011. And following the game that came out of research, we have at IBM 400,000 employees, more or less, and research is 1% of it, more or less. This game went out of research. The technology, Watson, that became a whole family of technologies, came out of research. And many organizations came to IBM and said, if you are doing so well in the game, why won't you help us in this business or that business? And many businesses came to IBM in a diverse range of areas. And the place where it seemed most urgent and important to assist was medicine. Because we do know that in the medical world, there are many very complex questions, and the answers might be hidden in a lot of literature, and it's hard for the human person to follow and read all these papers. So it's a very natural place was helping physicians in the world of literature. But I want to put it as a question because the regular, and that's learning from literature. But following that, before I put a question, following that, IBM decided, and Ginny Rometty, the CEO of IBM, said, I'm picking healthcare as our moonshot. That's where I'm going to invest a vast amount of money and allocate a lot of resources. And according to the press, the investment since April 2015, when we launched a business unit called Watson Health, is at the order of, do you know how much? Are we talking in millions or billions? Billions. But it's not 1 billion. The estimates, according to the press, is $5 billion, $5 milliard of investment in order to grow the business unit of Watson Health. And this is mainly in acquisitions. And the acquisitions has to do with patients' data. So if we want to be able to provide solutions that assist physicians in addressing all kinds of special conditions, we need to learn from the history. And when we learn from the history, it's the history of patients that is mainly recorded in the electronic medical records, as was discussed, I guess, this morning. And the electronic medical records contain information of the medical treatment that we obtained. And in the US, because there's a difference, unlike the Kupot in Israel, unlike the HMOs in Israel, there's a difference in the US between the provider and the payer, the insurance, who provides insurance and pay you for the expenses. And the payer has records called claims, where you keep all the claims, all the requests for reimbursement of the expenses of healthcare. So we acquired a company called Truven Health, who works with insurers and collects data. Do you have an idea how many individuals' data do we have in Truven, according to our agreement? So that's a US company based. We have access to 200 million individuals, data from 200 million individuals that has to do with claims. Some will claim that these claims are not clean enough or informative enough in order to learn about patients' data, but they contain some signals. That's one part. The other part is where we acquired Exploris, a spin-off of Cleveland Clinics, that collect data from EMRs. There we have 67 million individuals in the data, which is very impressive. For other reasons, our Kupot in Israel are unique because they are providing care in outpatient and inpatient in the clinics, מה שנקרא בקהילה ובבית החולים. I'm using the Israeli terms because there are no real equivalent US terms. So, but these acquisitions enable us to change the world of medicine. And the way I see it is the IoT, the amazing technology we saw here, who can interact with us, can collect a lot of information about us and changes the world in some ways. But the major engine for growth of success in healthcare in the past few years and in the future, in the next 20 years, in my view, is the ability to analyze patients' data and to learn from history and provide novel solutions. And to understand how unique it is, I want to quote the New England Journal of Medicine, the well-known journal where all the physicians look at it as the best place, the best venue to publish. And this New England Journal of Medicine had a paper in 1997, not so long ago, although many people here are very young, but not so long ago. And in that paper, they say if you read something in a journal, a study that is not randomized clinical trial, is not comparing in a randomized setting one group to another, you can throw it away. It's not informative, don't use it, meaningless. The world has changed drastically. There are so many papers that people read very cautiously on retrospective studies, going back to look at patients' data and learn from that. And this approach is totally forgotten and omitted, and even the New England Journal of Medicine later shared another paper that compares, in 2000, another paper that compares what you can learn from patients' data and what you can learn from clinical trials data. And in the conditions where you have sufficient information, they show that you mostly arrive at the same conclusions. So there's no reason to restrict ourselves to the standard way of development of medicine, which is we found a new molecule. We think it might assist patients. We are going to divide the world into this group who is using this molecule, other who are not, and learn from that. No, that's not the case. Technology and the ability to learn from patients' data is the way nowadays to make huge progress in the world of medicine. And because I'm here between you and lunch, I'm going to shrink a bit my talk, not to take too much time. And I just want to share with you because I'm going to do a very quick quiz, so please stay with me, stay tuned. It's a very quick set of questions on technologies buzzwords. I'm just curious how many of you are familiar with the different buzzwords that at least where I'm standing and where the people I meet are hectically being used. So have you heard about machine deep learning, causal inference? Okay, we're starting to shrink the population. So what I want to share with you is that indeed in the recent years it became obvious that it's not sufficient to have statistics. You want to use machine learning. And I'd like to provide you a very brief definition of machine learning. There are many different ways to define machine learning. I'm going to quote my advisor at UC Berkeley when I did my postdoctoral studies. His name is Michael Jordan. He's not tall, he's not black, no. Not that guy, a different guy. An expert in statistics, a famous, well-known thought leader. And in his view, machine learning is the combination between statistics and computer science. Because when you are looking into statistics and you want to understand some patient's data, you want to leverage as complex statistical model as possible. And you only have the vehicle, what you can use is your computer. So you want to keep in mind, what can I write as an algorithm, and then to make it more and more complex, but still to have a feasible algorithm that infer what you assumed on the data and learn from it and learn from the data. So that's the combination of the ability to write the algorithms and design them with complex statistical models. That's the machine learning. And the arrow here represents some division of complexities. So I guess all of you are familiar with descriptive statistics. We read it in the papers all the time, and when we want to understand something about, I'm going to quote a study. Don't ask me where it was, but I got very interested in that. I think, how many here know about the recommendation of 10,000 steps a day? Okay, it became very, very common. And it's supposed to help keep us very healthy. So there's a study that says, we looked at people who are doing an hour of exercise a day, people who are not doing any exercise, and people who are doing exercises of running at least an hour, 3 days a week and more. So there's the extreme athletes comparing to regular people, not real athletes, but the extreme athletes who run at least 3 times a week and run for more than an hour. There's the regular people, hopefully nowadays regular people, who are walking every day or doing some exercise of an hour a day, which is the highly recommended approach. And there are those who are sitting and not doing, letting go for all these recommendations and just not doing any exercises. So when you look at these 3 groups, they showed life expectancy. They were able to follow these people retrospectively, to get data from these people for several years. And they looked at life expectancy, and what do you think? Who had the best life expectancy? The extreme athlete? Yeah, not the extreme athlete, not 3 and more of running. Those who kept a very regular and steady and simple and not extreme, they had a longer life expectancy. What can we learn from that? So I guess it's sort of self-explanatory what we can learn from that. Let's not be extreme with anything, but that's, yeah.
There is one catch there.
Yeah.
One of the psychologists around this research, they say the guy which is 3 times a week in the gym or in the other 4 days, he is speaking to his wife. He has a good relation with his wife.
So you maintain healthy. Yeah, I saw that. That you have a lot of biases, because when you look at this group, there's some bias, because why do they keep such a healthy lifestyle? Maybe they keep a healthy lifestyle in other aspects in their life as well. And I gave this example because I think it's a good example to look at the whole complexity of descriptive statistics that might be informative. You just describe the different groups and you learn something from that. But definitely it's not accurate enough. And I don't want, if I need to get a treatment that will either save my life or kill me, I don't want to use only descriptive statistics. When it's this very shallow lifestyle recommendation, fine. But when it's a matter of live or die today, it's a different question. So then we would like maybe to have an hypothesis and to test it, and that's the standard statistical approach. But there are more complexities and other ways in order to, when you have retrospective data of large cohorts, you might want to cluster the patients to analyze similarities between them, develop predictive analytics or deep learning in order to be able to predict what will happen, and then to say, if I have a good prediction, it might mean that I captured something real in the data and I can tell what will happen. But that's not good enough. You might want to learn about the different interactions. So if I talk about, and I have here an example, I will give you one more example. I don't look at the time, but I will give you one more example of something that we are doing, and that's about HIV. I will give you the full story soon. But with respect to HIV patients, in the past it was fatal disease. You had HIV, oh my God, that means you need to say goodbye to all your friends for in few years at most. There's no other option. That was the 80s. But then it's an amazing disease because it also had all kind of politics attached to it. But let's put it aside. That was the 80s. In the 90s, in 96 actually, it was found that if you get a cocktail, the combination of drugs, you can save the life, and you can, the disease became chronic disease, and you can get a cocktail after cocktail. When this is not effective, you change the drugs and so on and so forth. So the patients are on drugs all the time, but you can switch the treatment and you are under control. The virus that infects the person and the level of the virus in the blood can drop into minimal, below detection level. So that was the story of HIV. Now, when we think of what will be the best treatment for a person at this point, we can ask ourselves, can we predict to the outcome what will happen if you take this cocktail or that cocktail or that cocktail? And based on the prediction, if we have an accurate prediction, we can say, according to our prediction for this person with this history, with these viruses, getting this cocktail will give you this outcome, a different cocktail will give you a much better outcome. That's our recommendation. That's a simple approach, and that's a prediction and deep learning approach here. But if you think about it for a moment, you need to take into account more complex world. It's a chess game, because I will give this cocktail and a resistance will be developed. Maybe I need to give a different cocktail that the immediate reaction will not be as good as I want it to be, as the alternative might be, but it leaves me with more options for later treatment. Do you see the chess game here? It becomes much more complex. So reinforcement learning is the ability to learn in a changing world and taking into account the next step as well as a reward that addresses the full story of the whole next few years, all different multiple treatments. Causal inference says that maybe I learned a lot from the data, but I always have this concern that I might have captured something that is unique to this data and doesn't captures the real relationships, the causal relationships of what is the influence of the success of the treatment. So I see a prediction and I know that with this cocktail, I predict this outcome, with that cocktail, that outcome. But I might have missed some causal relationships here, and it might reflect a particular relationship in the data. A very classic example for that is if people are getting cocktail A that is much more aggressive with toxic side effects, and cocktail A is very effective, but because of the toxic side effects, you only give it to those people who are very ill. And those people who are very ill, meaning they are with the disease for many years, their virus is resistant to many other drugs, maybe their symptoms and conditions are not that good, you only give it to this subpopulation. So when you look at the whole group, you'll see that in total, the outcome for this treatment is not as good as a different cocktail that might not be as good as this one, but is typically provided to naive patients, those who are the first time getting treatment and are going to react very well to whatever you will provide them. When you learn from data, you will see that cocktail A that was very effective actually doesn't look that effective because it was provided only to those very challenging patients, and cocktail B that is not that effective seems very good because it was always provided to an easier patient in a sense. Now when comes a new person and you predict the outcome, you will predict that with A, it's not going to be as effective as in B, just because in the data you had these biases. But if you inferred causal relationships and you learned what is the actual reason that this one was more effective and this was less, then you can come up with much more advanced conclusions. So causal inference is a set of technologies that are needed and important. And I would say that this error shows also the level of maturity in the community, in the scientific community. There are a lot of methods all up here, but here you'll find it's much more dilute. What set of tools can you use and how you're going to use that? I'm about to finish. I saw the sign. Decision analytics is the very last thing, because as we know, and I'm going to, as we know, when we want to provide the technology, and what you see here is one slide that tells a lot of story. That's why we're dwelling on it for such a long time. When we develop technologies in IBM research that needs to assist physicians, we have people with these skills from the medical world, from psychology, economy, and game theory, because these are the fields at which research is developed to assist in creating decision support systems and to support decision analytics. Because even if we know how to predict outcome and we have the good technology, it doesn't mean that we did our thing and we are ready to go. There is a known study that Professor Daniel Kahneman refers to about patients who were told that, a study that was performed in reality. Patients who were told that they have 90% of survival with this cancer that they were just diagnosed, and people in the next 5 years, and people who were told that they have 10% of dying in the next 5 years with the disease they were just diagnosed. Their perception of the risk and what they are going to suffer from the disease was very different. When the word survival was mentioned, they were much more optimistic. When it was about dying in the next 5 years, they had very different reaction. So if they had to decide on a treatment, it's very important how you pick your words and how you recommend what you have to recommend. And that's why these are other fields of areas where we take into account when we want to assist patients. I'm going to finish with a quote. You see that I wanted to share more, but I'm going to finish with a quote from the Emperor of All Maladies, Siddhartha Mukherjee, Dr. Siddhartha Mukherjee. Anyone here heard about this book, The Emperor of All Maladies? Sartan Melech Kol HaMachalot, something like that. It was translated to Hebrew. No? So this guy was a physician, is a physician, sorry, not was. He's a physician from Mount Sinai who wrote a wonderful book about cancer. And when he writes about cancer, he also talks about what medicine is. And he says that, that's his book, and he says that medicine begins with storytelling. Patients tell stories to describe illness. Doctors tell stories to understand it. Science tells its own story to explain diseases. And I brought this because I think it's a very nice way to capture what medicine is and also to understand how medicine is changing. Nowadays, we have technologies that can read stories, that can understand sensors, can look at images. And all these technologies are going to digest the stories that come from in many different forms and make it available for us in the form of apps or other services that can provide us better care. Thank you.